This is Algebra 2, Unit 12, Lesson 6 on multiplying probabilities. Now, probabilities involving single-stage experiments are easy enough because only one thing is happening to affect the probability. So, for example, you flip a coin, you pick one person at random, you pull a card out of a deck. But probabilities, both empirical and theoretical, become increasingly more complicated with multi-stage experiments where more than one thing happens. So, flip a coin 3 times, for example. How we handle these types of probabilities actually comes from the conditional probability formula. Okay, so given that the probability of event B occurring given that the probability of event B occurring given event A has occurred is probability of B given A is P of A and B over P of A. So if we rewrite this formula solving for P of A and B, basically cross multiply, P of A and B, remember and is the intersection, is equal to P of A times P of B given A. So if we take that formula, cross multiply and solve, we get that. So how could we write this formula if events A and B were independent? Well, we know that P of A intersection B, the overlap, is equal to P of A times P of B. So there we go. All right, so this rearrangement of the conditional probability formula gives us a useful tool for calculating the probability of events that occur in multi-stage experiments. You'll easily be able to accomplish this if you systematically phrase the questions as union events connected by and. All right, let's take a look at some examples. Consider the spinners shown below. The spinner is spun twice, so it's going to be spun once and then spun again, and then the result is recorded. Are the outcomes of the two spins dependent or independent? Well, does spinning the first time affect spinning the second time, the probability? No. So they are independent. Okay, they are independent. What you get on the first spin does not affect the probability of the second spin. What you get on the first spin does not affect the probability of a second spin. So you're still going to have the same probability every time you spin. There we go. Okay, so what is the probability that you will get an even on the first spin and a number greater than 5 on the second spin? Okay, so we want probability of getting an even and a number greater than 5. Okay, so let's take a look at the probability. It would be the probability of an even times the probability of a number that's less than 5. Okay, so we need to figure out the probabilities of each of those. What is the probability of getting an even number? Well, let's see. We have 1, 2, 3, 4 even numbers out of 8. So your probability is 4 out of 8. Okay? The probability of getting a number less than 5. Okay, so a number less than 5 would be 4, 3, 2, or 1. Greater than 5, I'm sorry. Got the wrong one. Greater than 5. All right, would be 6, 7, or 8. Okay, so greater than 5 would be 6, 7, or 8, so that would be 3 out of 8. So when I multiply those together, I get 12 out of 64, which will reduce to 3 out of 16. Okay, so when you are doing the two probabilities with an and, basically you multiply the separate probabilities together. All right, what is the probability that you will spin a prime number and a perfect square in either order? Okay, now that's very important, in either order. Note that this is more complex than B. All right, so we have to consider two possibilities. You could get the probability of getting a prime first and then get a perfect square. So your first spin could be a prime, your second spin would be a perfect square. Well, couldn't you get a perfect square first? So, or you could get the probability of a perfect square and then get the prime. So there's actually two separate probabilities here, and they're connected with an or. Okay, so this is an and, so the probability of the and the probability of the and here, and then we have probability of an or. Well, what do we do with the probabilities? Well, or means you add. So the probability of the prime in a perfect square, we would multiply the probabilities. And means multiply, or means add. All right, so and means multiply. So the probability of getting a prime number. Well, the prime numbers would be 2, 3, 5, and 7. So there's 4 out of 8. And how many perfect squares are on this spinner? Well, there's only one. 4 is a perfect square, so it's going to be 1 out of 8. All right, now the probability of getting a perfect square first. Well, again, perfect square is going to be 1 out of 8. And then a prime is still going to be 4 out of 8, but we got them in a different order. So you could get it this way, or you could get it this way. So when I multiply them together, I get 4 out of 64, also 4 out of 64. So your probability is actually going to be 8 out of 64 or 1 out of 8. So that's your probability. You have to take into account when you're doing a multi-stage step the different ways you could get the combinations that you want. So because we said in either order here, it's not just the prime and the perfect square. If you got the prime first, then the perfect square, or you could get the perfect square first and then the prime. So also when you do this, when you're doing an and means multiply the probabilities, or means add. Okay, so and means multiply, or means add. All right, now as experiments grow more complicated with more stages, theoretical probability becomes increasingly more complicated. It is especially important to note whether you are sampling with or without replacement. So that makes a difference when you are pulling your probabilities, if you put something back. All right, so let's look at exercise 3. A class consists of 12 girls and 8 boys. A group of 3 is picked to give a speech. If the students are picked at random, what is the probability they will all be boys? So use the event below to show you how you calculated your final answer. So event 1 will be the first picked was a boy. Event 2, second picked was a boy. And event 3 was third picked was a boy. Okay, so let's think about this for a second. When you give a speech, can the second person that is picked give this first speech? No, it would be each one is going to be an individual probability. So the probability of event 1 that the first student picked as a boy, well, there's 8 boys out of how many total in the class? Well, there would be 20. So it would be 8 out of 20. Okay, now, in event 2, the first student picked can't be picked again because he's already giving a speech. So, how many boys are there now? Well, there will only be 7 boys, but out of how many total students? Well, it will be 19 students because this is now the probability of E2 given that you have E1. All right, so you have to take into account what happened in E1 to do E2. So that's going to be 7 out of 19. All right, and then the probability of getting the third boy. All right, the 2 boys have been picked already, so now there's only 6 boys and a total of 18 students to choose from. All right, so this one is actually going to be the probability of E3 given that you had E2 and E1. So there we go. So there's your 3 probabilities. Well, so we want to figure out the probability of getting 3 boys. So we want the probability of E1 times E2 times E3, because probability of getting 3 boys would be first boy, second boy, third boy. So it would be 8 out of 20 times 7 out of 19 times 6 out of 18. So when I multiply all these together, we do 8 times 7 times 6 is 336. And then 20 times 19 times 18, do my calculator, 20 times 19 times 18, which is 6840. So this is 336 out of 6840. Now you can leave it like that, or you can reduce it. It's 14 out of 285, or if you divide it out, so it would be 336 divided by 6840. It's about 0.049, so about 5%. So equals 0.05 or approximately 5%. Okay, so the separate probabilities we had to figure, but because we didn't replace the boy, you have to take into account that the number of students for the ones you want and the total will be reduced each time when you do that. All right, the multiplication property of probability is crucial in many applications in engineering decision making. So say that a power generating facility has 3 primary safety switches in case of an emergency. The probability that any one of these switches would fail is 5%. What is the probability that all 3 will fail, given that the switches are independent of each other? Okay, so if switching off one doesn't affect the other, that's what that means. Okay, so the probability of switch 1 failing, well, that would be 5% or 0.05. And switch 2, so we would multiply the probability of switch 2 failing would be, well, does the 5% fail affect the second one? Nope, that's still going to be 5%. Still going to be 5%, and then the third one and the third switch failing is still going to be 5%. So when I multiply 0.05 times 0.05 times 0.05, all right, it's 0.05 cubed, which is 0.0125, so 0.00125. All right, so that's approximately 1.25%. All right, so because the results are independent, the percentage doesn't change between each event, so that's why it's independent. The previous one, the percentage changed because we didn't replace the boy, so the two events were not independent. Okay, let's take a look at the last one. Many times when using the multiplication rule, we need to be careful about how we frame the question. But if we properly frame it in terms of and or logical connectors, then the rules of probability will work out. All right, let's look at exercise 5. A company was determining the effectiveness of its warranty sales on computers. They took data on the number of customers who purchased warranties on 2 different brands of computers. If a customer was chosen at random, what is the probability they did not purchase a warranty? Okay, so we need to figure out the probability they did not purchase a warranty. So let's look at our columns here. We have type 1 and type 2, the 2 different types of computers. And then this is the percentage of the customers that purchased the computers. And this is the percent of those who purchased that also purchased the warranty. So this is how many purchased the computers. This is how many purchased the warranty. Okay, so we want to figure out what is the probability they did not purchase a warranty. Okay, so let's think about this for a second. What could you have done? Well, you could have bought type 1 computer and then not purchased the warranty. Okay, or you could done a type 2 computer and not purchase the warranty. So those are 2 separate things. So we want to figure out the probability of type 1 and no warranty, or the probability of type 2 and no warranty. Okay, so there's 2 separate probabilities here. Okay, so we have to figure out, first of all, the probability of type 1, picking a type 1 computer with no warranty. Okay, so how many purchased the type 1 computer? Well, it says 68%. Okay, so that's type 1, 68% right there. Now, it says percent of those who purchase it also purchase a warranty is 35%. So if 38%, 35% purchased the warranty, how many did not? Well, remember, not purchasing would be from 100%. So it's 100% minus 35 would be 65% did not. So no warranty will be 0.65. Okay, so or, which means to add, to how many purchased type 2 would be 32%. So 32% picked the warranty, so that would be, or purchased a computer, so that would be 0.32. And of those 32%, 56 also purchased the warranty, so how many did not purchase the warranty? So it would be 100 minus 56. All right, and that would be 44%. Okay, so if I multiply these out, this comes out to be 0.68 times 0.65. Is 0.442, and then 0.32 times 0.44, so 0.32 times 0.44 is 0.1408, so this is a total of 0.5828, or approximately 58.28%. Okay, so multiply probabilities.